You're blocking the
All righty. Let's see where we're at. Hopefully you guys are making progress on your homework. Just we have another week. We'll have our usual problem session next door tomorrow at 1 o'clock. So I just want to remind you that we won't have a lecture a week from today. So we'll have to think about that at some point. All right, so let's quickly sort of review some of the things we talked about last time. So we're talking about the Wigner function, which is a quasi-probability distribution that's an example of a phase-space representation. And we care about this generally in quantum mechanics because it is a way of us understanding the distinction between quantum and classical physics, when we're going to, and we'll say a little bit more about that in this lecture today, in thinking about how classical dynamics differs from quantum dynamics. And as classical dynamics, we can think about it in a phase-space dynamic. We can compare our quantum and classical descriptions if we have a phase-space representation in quantum mechanics. In quantum optics, it's particularly important because the classical theory of light is electromagnetic waves, and the electromagnetic waves are, we think about them in terms of complex amplitudes, and those complex amplitudes are our phasors, which have a phase-space picture. So that's why we particularly concentrate on it in quantum mechanics. So a lot of the work that was done in the early days by Wigner and others was kind of ignored, except in quantum optics, and now it's kind of become a thing again. All right, so that we define the Wigner function in terms of the projection. We have an operator basis or operator frame, which are the set of operators that are symmetric delta functions on phase space as we've defined them, okay? So that's the definition of the Wigner function. We're just projecting the operator onto something that looks like a point in phase space as best we can do in quantum mechanics, okay? It's not really that, because this, as we know, is not a positive operator as we've discussed. Right, so when we express in terms of the complex variables, the complex amplitude, and A and A dagger instead of X and P, we write it this way. So generally speaking, we call the Weil symbol as the projection of the operator onto the symmetric delta function with the proper normalization, okay? So the Weils, for every operator, we can define its representation in phase space by projecting it onto the symmetric delta function, okay? And the Wigner function is just the Weil symbol for the density operator with this convention, 1 over pi. Not everyone takes this convention. This is the standard convention. So that this pi is chosen such that the Wigner function is normalized when we integrate over the plane. Sometimes this is written as, with the measure 1 over pi, it's just a different choice of how we choose to normalize, okay? So with that, you know, given the Weil symbol for any operator, we can write the operator as a superposition of the symmetric delta functions weighted by the Weil symbol, okay? Very good. And so this gives us a picture, for example, if we wanted to have a way of calculating, say, the expectation value of some observable, some operator, which is given by the trace of the operator with the density matrix. In phase space, it looks like what we would do classically. We have some random variable, and we have some function of that random variable and we want to look at what its average value is, we would average it over the probability distribution. Here we're averaging it over the quasi-probability distribution. But it looks just like what we would do classically. Okay? Now the other thing we didn't prove, but I mentioned, proving it's not that easy. Only very recently did I actually look at the proof of Hudson's theorem. But what Hudson's theorem tells us is that if rho is a pure state, then the Wigner function is everywhere positive if and only if this is a Gaussian function, okay? So there's some intermittent relationship here between Gaussianity, Gaussian statistics, and sort of classicality. We'll come back to that. It's a very interesting point. I want to emphasize this relationship between positivity and Gaussianity is only true if the state is pure. We can certainly have a statistical mixture of states, which is, you know, I can have a statistical mixture of coherent states that's not Gaussian distribution, but everywhere positive, okay? But if it's pure state, then it has to be Gaussian, okay? All right, so at the end of last lecture, we were talking about the idea of I guess I should say, so we talked about 3 different phase-space representations. We have been talking about the Wigner function, but of course, we talked about, for, you know, kind of memorial, the Glauber-Sudarshan P representation, where this was defined such that the state was not a superposition of the symmetric delta functions the way I've written it over here, but was a superposition, or not superposition, but a statistical mixture of projectors onto the coherent state. So we thought when we wrote this down, it's because we were thinking about a classical picture where we think about, we have each of our possibilities of a classical state is a coherent state, but if I have some kind of noise, and say the current that produces that field, then we would say the state is a statistical mixture of those classical waves. So when P was a positive function, that's what we have defined to be definitely classical light. There's a definite classical description in terms of classical current producing classical fields. Okay. We also, at the end of lecture last time, defined, so this is the Wigner function. This is the Glauber-Sudarshan P representation. And then we have the Q function, which is a natural thing to think about if we just thought about wanting to define a probability distribution on phase space. Well, we can't define it in terms of a projector on X and P at the same time because there are no eigenstates of X and P at the same time. But maybe the best compromise to that is the coherent state, which is not really an eigenstate of X and P, but it's an eigenstate of A, which is X plus IP over here. And so that's a kind of natural thing to think about in the probability distribution. This is the diagonal matrix element, that's a probability. If you want to normalize it, we divide by pi, and then it will, as all of these guys will be normalized over the waveform.
Is it correct to say that the Glauber B representation is related to photon counting the same way that Wigner's related to quantizing?
It is, absolutely. So that's a very good point, and we'll re-emphasize that in just a bit. So this is what we call the Husini distribution. But as we were discussing at the end of lecture, all of these representations are different sides of the same coin. And they are related to the story of representations depending on operator ordering. So, you know, what makes quantum mechanics special? What's the secret sauce of quantum mechanics? We discuss this, we argue this, we debate this for decades. But obviously one aspect of what's different in quantum mechanics is the fact that different operators don't commute, and because they don't commute, there's something going on there. And that point comes into the fact that we have these different representations depending on how we order operators.
Would it be kind of like in the spirit of this to say that normal ordered operators are like classical-ish in a sense? Because within a normal ordering, they all.
So yeah, let's come back to that. Let's think about this in just a little bit. But yes, there's a lot to be said about that. So let me hold off on both your question and our expression, which are interrelated. Okay, so the way that we did this is we said, okay, if I have some operator A, which is some function of A dagger, then I can write this as an operator ordered power series. So I'm going to have some coefficients where I'm going to commute things in such a way that all the A daggers are on the left and all the A's are on the right. And there's some coefficients. I could alternatively put all the A's on the left and all the A daggers on the right. That is an anti-normally ordered series. These are the same operator. I just commuted things in such a way, as we discussed last time, and they're going to be different coefficients here. Okay? Or I can symmetrically order. Where the symmetric order is, I look at all possible permutations and then divide by the number of possible permutations, okay? So I write them in totally symmetric order. These are all the same operator, but they have different coefficients because A and A dagger don't commute, right? So I can define what we call S-ordered. And now you're stuck with my stubbornness of the opposite notation that everyone uses. But we're going to use this. So, S equals plus 1 will be normal order. S equals minus 1 is anti-normally ordered. And S equals 0 is symmetrically ordered. So that we define the S-ordered representation as so this function will generally be different depending on S. Even though they all represent the same operator, they're different functions. Everyone clear on that? So all I did is I replaced A dagger with alpha star and A with alpha, okay? This is, if I start with the operator and I either symmetrically order it, anti-normally order it, or normally order it, and then replace this, then this is the S-ordered representation. I choose this representation so that for this very reason, this is why I choose this notation, because it is the thing that when you do this ordering, you get this function. Okay? All right, so I claim, we will prove this in a little bit, that this is equal to the trace of A with the minus S ordered delta function. This is why my definition is the opposite to everyone, but I think it's important to do it this way for reasons that I'll try to emphasize because of the duality between the S and minus S orderings, okay? So if I want to find the S-ordered representation, I project onto the minus S ordered delta function, okay? So let's just, what do I mean by that? So, T0 is the one we've seen before. Symmetrically ordered. I'm sorry, symmetrically ordered delta function. T plus 1 is put all the A daggers on the left and all the A daggers, the A's on the right. Okay, so that's the normally ordered delta function. And the anti-normally ordered delta function is the other way. I put all the A's on the left and all the A daggers on the right. Okay. So, the thing we'll show in a little bit is that the following things are true. If I look at the inner product between the delta function, these symmetric delta functions, actually these all have a pi, I should say. If I look at the inner product between these guys, which is the trace of this, these guys are Hermitian, so I don't have to worry about the dagger. Let's say for alpha prime, that these guys are orthogonal. But notice we have this duality. Okay, so there is a dual vector in the operator space which is orthogonal, and it's with the opposite ordering. If this is normal ordered, it's orthogonal to its anti-normal ordered prop, in this case. It's also complete, but in this dual sense. We'll prove these things in a moment. I'm just stating some facts of nature. Okay. So we remember, we've discussed in the past that the delta function operators form a complete operator basis, and they form a resolution of the identity. The S-ordered delta functions are an operator frame. The notion of a frame is a more general notion than a basis. It's a complete set of states, but aren't necessarily linearly independent or orthogonal. But there's a sense of, there's a dual vector that is orthogonal. In this case, the thing that's dual to this is a thing with minus s. Okay? Yeah?
Is the symmetric delta function Hermitian?
It is. They're all Hermitian. Yes, indeed. And in the same way that a regular delta function is a real number, even though it's the Fourier transform of a plane wave, which is complex. Okay? Kind of interesting. Yeah?
So then what's the difference between the T0 and the T-1? Delta is Hermitian.
This guy
Yeah, and then the
versus this guy.
Yeah.
Well, this guy, I factored it out. All the A's are on the left, and all the A daggers on the right. This guy, I can't write as a product of
Oh,
those
right,
two
okay.
things, because A and A dagger don't commute. Yeah,
You have a dagger on our delta over here.
nah, yeah, God knows, yeah. Indeed, thank you. Yeah,
What's, no, never mind, sorry.
all right, we'll continue. Yeah, Omar.
Are they also called weak and anti-weak ordering?
Wick and anti-wick? Maybe. It's not something that I'm familiar with. Yeah. But we will check. We'll ask ChatGPT. I used to ask Siri, but she asks ChatGPT now, so. Anyway, all right. So with this said, we have some interesting things. If I look at this, for example, if I look at the expectation value of some observable, which is the trace of row with A, I can write this using my completeness relation. Okay, so this is the inner product of row with A in operator space, vectorized. Everyone clear on that? That this trace is just the inner product between row and A in operator space, which I can write like that, which is equal to let's look at that expression and compare it to what we had up on the board for the case when we wrote this for the Wigner function. If we look at the trace inner product between two operators, in this case the density operator and the other, that trace inner product is the integral over space of the Weil symbol for one operator with ordering S, and the Weil symbol for the other operator with ordering minus S. There again is this duality. If I want to look at the expected value of an observable, I have to look at this dual operator ordering. I look at the Weil symbol or the S-ordered Weil symbol for the operator A and minus S for the other operator. In this case, I define the S-ordered thing as the S-ordered representation over pi. Okay. Let's look at something that can maybe give us some relations here. Consider the anti-normally ordered delta function. Okay. Now, if I look at that operator, I can actually, there's a very beautiful way of expressing this in terms of the coherent states. So let me insert a complete set here. I'll use a different dummy variable, call it gamma, where these are coherent states. We know that this is a resolution of the identity on Hilbert space, right? Let's plug that in. That's equal to, the pi's cancel, integral over the phase space, this delta function, and then this delta function. Right? So now what? The coherent state is an eigenvector of the annihilation operator. So I can just replace the annihilation operator by its eigenvalue. Similarly, on the bra side, this is an eigenvector with eigenvalue gamma star. So this is equal to the integral d squared gamma delta gamma minus delta gamma star minus alpha star gamma project. Okay, I just replaced these by their eigenvalues because these are coherent states, which are eigenvectors of any data. But this is just a 2D delta function on the phase plane. And if I integrate that, I get something really beautiful. That the anti-normally ordered delta function is, in fact, the projector onto a coherent state. I know. Omar's reaction was exactly the other one. You're like, really? Wow. So that's interesting. So with that said, we can now look at the different, if I look at the row 1, the normally ordered representation of the density matrix, I get that by tracing with the anti-normally ordered delta function, as we said, right? That's the definition of the representation. But what is that? Well, I can plug that in. Which is the Husini distribution up to a factor of pi. Moreover, if I look, we said from this completeness relation, in the same way that I wrote the density matrix as a superposition of the symmetrically ordered delta functions weighted by the Wigner function, more generally, I can write I want you to stare at this and stare at this. They're the same thing, but now with this duality, S and minus S. As S was 0, we got this. This, again, follows from the completeness relation that we had before. This relationship is the whole story. We'll come back to that and prove it in a moment, okay? So, for example, no. Oh boy. All right, George. Start again. So, what we said was that rho sub S is the trace of rho with T sub minus S. Okay? And this is, if I divide by pi, this is W of S. Okay? Very good. So, with that said, let's look at, if I look at rho, I can insert a complete set. Like that. Yep.
What we've done here at the bottom left corner
Yep.
of this blackboard is we've generalize the while symbol.
That's correct. And by definition, this is my forced definition. I'm saying that the S-ordered representation is the trace with the minus S-ordered delta function, because this is the thing that gives you the S-ordered power series. Okay? Yes, Ben?
Your definition, is that the only difference in your definition? Like, does plus S still signify the normal order?
No, so in most textbooks, people will call this W sub minus X. You take the trace with the same thing. I'm defining it like this. The S-ordered representation is the trace with the minus S-ordered delta function.
Right, but do plus S and minus S mean the same thing?
Not sure how others define it, but
Okay.
let's not worry about it. Stick with this definition.
Which is the ordering of the delta function and that you use and
Yeah.
the ordering of the final result are
Yeah.
the same. They're either both symmetric or both normal or both empty.
So again, let me try to clarify things. I'm sorry to make this confusing. I have defined this. The S-ordered representation is what you get from the S-ordered power series replacing alpha A by alpha and A dagger by alpha star. That's my definition. That's how I'm defining the S-ordered. What is true is that is attained by tracing with the minus S-ordered delta function. I define it this way because it gives me the right ordering of the power series. Okay. So with this is equal to W of minus S of rho. Let me do it the other way around. Let me put this a plus, this is a minus, and then this guy is a plus. So this tells me that rho is equal to the integral over the phase space W sub S with T sub S. Okay. Because this is with minus. Okay, so let's put this together. Let's look at, for example, rho is equal to that, according to this definition. We just said this was equal to the projector onto the coherent state. So what the heck is this function then? What do we know? No, it's not the Q function. What function?
This is Deutsch.
This is the P representation. By definition, the P representation is the thing that when you look at the superposition of that, so the P representation. So what we have is the following. The Wigner function is the trace with the symmetric delta function. So this is equal to the the symmetrically ordered representation of rho. We also just saw that Q was equal to the trace with T minus 1, right? Because T minus 1 was the projector onto the coherent state, which is the normally ordered representation of rho. And the P representation is the anti-normally ordered representation of rho. So they're all three representations are just different operator orderings. Very good. We'll come back. Okay, so I want to come back to a little bit of the questions that both Tristan and Arik asked earlier. Do you have a question, Omar?
So there will rho equals d square of p of x alpha alpha. And
I'm sorry, where?
right way.
Here?
Yeah. So if we write rho same way, but with q, how would that look like?
Interesting question. So how would that look like? What we have is that the Q function would be equal to rho would equal the Q function. Since this is the normally ordered, we have to have the normally ordered.
And t plus 1 is not alpha.
No. T plus 1 is, where is it?
It's off of the bottom board behind.
Dual?
It is orthogonal to this, but if I were to insert a complete set of coherent states in here, that wouldn't work.
I feel deceived.
What's that?
I feel deceived. I thought I wanted alpha.
So, it's interesting. It's interesting. We're going to absorb, there's a lot to absorb here. So, firstly, I want to emphasize these facts. The Wigner function, the Q function, the P function are all representations of the density operator with different operator orderings. The Wigner function is what we get from the symmetrically ordered series. If we normally ordered, we get the Q function, and we obtain that by tracing with the anti-normally ordered delta function. And if we wanted to get the P representation is the anti-normally ordered power series, and we obtain that by tracing with the normally ordered delta function. Okay, so let's continue here. I wanted to say the following thing. Suppose I have an S-ordered product of A and A dagger. Okay, so if S is 0, it's a symmetric order. If F is plus 1, it's this. If S is minus 1, it's the other thing. What this is equal to is, if I look at the expected value of, let's call this O, S, the expected value of this will be equal to because of this duality, O, S, alpha, from this duality that we had over here, the general expectation, where did we write it down? Somewhere we wrote this down. Yeah. Right? If I look at the expectation value of any observable, I can find that as the average of the representation of the S-ordered observable with the minus S-ordered density matrix or Wigner function. Okay, so what this says is the following. The expected value of a normally ordered guy is alpha star alpha to the m with the anti-normally ordered Wigner representation, which is the p function. And if I looked at the expectation value of an anti-normally ordered product, I get this, but averaged with the q function. And if I looked at the symmetrically ordered product, I get this with the Wigner function. So each of the moments, anytime I want to calculate a set of moments, I can think about whether those moments are normally ordered, anti-normally ordered, or symmetrically ordered. And I can obtain them in a classical-like way, which choosing the right ordering of the representation of the state. If I'm looking at normally ordered products, I need to look at the anti-normally ordered representation of rho, which is the p representation. If I'm looking at anti-normally ordered moments, I can take that in a classical-like way, but with the normally ordered density matrix, which is the Husimi representation, and finally the Wigner function. Okay, so I want to come to the two questions, and then I'll come to your question, Benny, in a moment. So what we see here is what we saw before when we talked about the Glauber theory of photon counting. Then the Glauber correlation functions looked quasi-classical with respect to the p representation. And whether we called our photon counting experiments ones that we can predict classically or not had to do with whether the p representation was a positive probability distribution or not. So this was what we saw for photon counting. In contrast, the symmetrically ordered moments are what we saw when we were looking at quadratures and when we were looking at homodyne measurement. So if we're doing homodyne measurement, then we can say our predictions of those measurement outcomes are describable from a classical statistical theory or not, depending upon whether the Wigner function is positive or not. Now, the Q function is a more complicated beast. It's everywhere positive, but the statistics of it aren't really telling me about the measurement in the same way. The fact that it's positive is saying that there is some measurement whose probability distribution is the Q function. They actually are heterodyne. We'll come back to that a little bit later. On the other hand, the moments of this are not telling us about any realistic process. So it's a kind of complicated beast here. Okay. Then you had a question.
Yeah, I'm just wondering, in our choice of normal order, anti-normal order, restriction, are we losing any information in row, or can we just get back to the more general row from just one of those?
Yes, any one of them determines the state. I mean, as we saw over here, given the Wigner function, I can find the state by superpositions of the delta functions. More generally, this is true. So for any representation, I can get back to the operator by this integral. Yes?
So I'm expressing my density matrix in that particular measurement basis?
That's correct. So, I mean, what we saw, it's not that we're, the measurement isn't necessarily in the number basis per se. It's just saying that if I do a measure, so what we saw in the Glauber theory is that the photon counting and the coincidence and statistical photon counting were related to the normally ordered products of A and A dagger. Okay. And what that is expressible as, it looks like a classical average over the classical random amplitudes that a radio astronomer might just write down with a particular probability distribution of those amplitudes. And we call that classical if this was an honest-to-God probability distribution. Similarly, if we look at the statistics of homodyne measurement and we looked at those fluctuations, they would look like the symmetrically ordered guys. Okay. Now, I want to come back, maybe Tristan, to your question. I mean, what we know is that there are states of light, like squeeze states, which have a Gaussian and positive Wigner function, in which case, from the point of view of homodyne detection, they look perfectly classical. But the P representation is actually highly singular, doesn't even exist as a well-defined function. And so from that point of view, the photon counting statistics are very non-classical. It's saying that there's sort of different hierarchies of classicalness. We can have a state which in some measurements we have a classical description, a classical statistical description, but other measurements we do not. What we also know, though, is if the P representation is positive, then all the other ones are also positive. And so in that sense, it's the most, if the P representation is positive, then every measurement we can possibly do has a classical description. Because as we've also discussed, the state of light which has a positive Glauber P representation is a state of light that comes from classical current. And so in that sense, it's totally classical. It's a totally classical description. All right, let's maybe show how some of this stuff, how we can prove some of these things. All right, so I'll be fancy. I use the word lemma. The displacement operator is the generator of operator ordered series. Okay. Let me explain what I mean. So let's look at the displacement operator, which is defined to be for a complex number beta, e to the beta A dagger minus beta star A. Everyone should memorize that, okay? You need to know what the displacement operator is. If I write this in a power series, then this is equal to the sum n times over n and m beta to the n minus beta star to the m over n factorial times the symmetrically ordered we'd see that because just from the binomial theorem, right? If I write the exponential as a power series and then I take one of these things to a power n and use the binomial theorem, I'm gonna get every permutation, okay? So this is number one, okay? The normally ordered displacement operator, so this thing with the colons is, you remember, the thing when we ignore commutators and we just put all the a's to the left, I mean a daggers to the left and the a's to the right. That is the normally ordered displacement operator, okay? We call this d plus 1 for s, for plus 1 normally ordered, okay? This, we can see if we expand each of these guys in a power series is equal to this, the normally ordered series in this way. These two operators don't equal one another, okay? This guy, I've turned off the commutators and just asked, if I turn off the commutators, there's this power series. And similarly, if I put the minus 1 and in my crazy notation, I put this is my notation for anti-normally ordered, you put the colons the other direction. And no one's looking like, what the heck? that's what I do. And that's equal to this guy. And get the same thing, but with the anti-normally ordered guy. Let's see, no, this is n, this is m, this is n, this is m, this is m, this is n, the way I've written it, okay? Now, from Baker-Campbell-Hausdorff, we know that if I look at the exponential of the sum of two operators, I can write this as the product of the exponentials times a quantity e to the minus a commutator b when a commutes with the commutator, and so does b. Okay. And that's true for these guys. And so what is true is that v of beta is equal to e to the minus a half beta squared e to the beta a dagger e to the minus beta star a, and it's e to the plus 1/2 beta squared with this in the other order. And so if I bring this to the other side of the equation, what I see is the normally ordered d with the two colons, is this times that factor, and this. So that tells me that the s-ordered d is equal to e to the s beta squared over 2 times the symmetrically ordered. It should. Let's see. Sorry. Correct. Okay, so that's interesting. So what that tells me I'm say, right?
Is that not diametrically opposed to the original definition? Isn't that just?
No.
No?
So if I look at this, for example, d plus 1 is e to the beta squared times d. But if I plug that in times this, I cancel that term and I get exactly what I said.
Okay, makes sense.
It cancels this term and gives me, this is equal to e to the minus beta squared over 2 times the normally ordered guy.
I see, so in all cases, that prefactor, sort of.
This, by definition, that prefactor takes into account the commutator. So, what we thus see is the following. Everyone see that? Because this is an e to the s times this and e to the times an e to the minus s, and they cancel. Similarly, we have this fact. So, because if I just plug this in, this has an e to the s, this has an e to the minus s, they cancel. And so I get, and since we showed this was the universe, so again, we see this duality. And we define the s-ordered delta function as the Fourier transform of the plane wave, or displacement operator, with that ordering. And so it follows from exactly the same arguments that we had before, that the s-ordered delta functions form an operator frame with this duality. If this is true, then this is true just by taking the Fourier transform. So this guy is a resolution of the infinity. Okay? Now I want to finally prove that I obtain my operator order series by the trace of the operator A with t minus s. Okay, let's show that. So again, A, some operator I've written in an s-ordered power series. D, the displacement operator, if it's s-ordered. Written over there somewhere. Beta to the n minus beta star to the m, n factorial, m factorial, times the s-ordered operator product. That's what we wrote up there. Those three D's are this. Depending on the ordering, they all have the same coefficients, interestingly, no matter what the order. Okay? So now, using this fact, I can find these coefficients using the completeness relation. Okay? So if I look at A is equal to, by this completeness relation, the trace of d dagger of s minus s ds. Everyone see that? That follows from this. The fact that the d's form a complete basis of operators means I can decompose any operator into a superposition of displacements weighted by their inner product. But now let's plug this in, okay? This says that this is equal to the sum over n and m integral over all space minus beta star to the m factorial m factorial. The trace, I already done that. So what I did is I plugged this into this expression. Okay. So look what I have. Here are my coefficients. Right. If I equate this to this, these are the coefficients. Now, no one in their right mind would ever calculate the coefficients this way. This is a formal expression for them. But notice, to get the s-ordered power series, I had to trace with the minus s-ordered delta function. Or not delta function, displacement operator. Okay, so now let's put it together.
So that entire expression you boxed is the coefficient.
That's correct.
Okay.
That
So
entire-
it does depend on the, okay, I see.
It's a function, it depends on the operator, we're integrating over this, but I have to get it by tracing with the minus s version of it, okay? So, what we just said, I defined the s-ordered representation as the power series where I replaced the A's with alphas and the A daggers with alpha stars. That's my definition. And let's plug that back in now. When we plug that back in, these coefficients, I get the sum, the integral over this, the sum over, I'll put the sum outside. I know, I'll put the sum inside. Integral beta. Beta to the n minus beta star to the m, n factorial, n factorial. I have alpha star to the n, alpha to the m, times the trace of the operator with dx. So I just plugged in for these coefficients that are boxed here. Huh?
Should that be dagger?
It should, importantly, yes. So now I'm going to, that's very important, now I'm going to remember that d dagger is d of minus beta. Okay, so I'm going to turn everything into a minus sign over here. And the integral over the same, over the measure, I don't, it's the same d squared beta if I change to minus beta. So let's write all this together now. What I have, I have the sum.
Sorry, why did those betas become inverted again?
Because d dagger is d of minus beta.
Right, but why did those betas in the summation?
Oh, because, yeah, now I wanted to change beta to minus beta. So I made the substitution now, beta goes to minus beta. And then I changed these signs. So I did two things. I'm sorry, I screwed up. Let me go into the steps. Okay, all I've done here is change the dagger of beta is to minus beta, and now I'm just going to substitute beta goes to minus beta.
Okay, yeah.
Okay, so let's make that a plus, that a plus, that a minus.
Okay, thank you.
Yes, thank you, everybody. I screwed up. That's correct. Okay, let's put it together. This tells me this is equal to an integral over beta, the sum and m, and then I'm going to get alpha beta star to the m over m factorial minus alpha star beta to the n over n factorial times the trace I could do these sums now. What are they, those sums? They're exponentials. So this whole thing is equal to e to the alpha beta star minus alpha star beta. Everyone see that? Because one of them has a minus sign.
Can you put them together?
Those are numbers. Alpha and beta are numbers.
Oh,
Alpha and beta are numbers. They're complex numbers. So, what we see is that this is equal to the trace of A with the integral over beta, d minus s of beta, e to the alpha beta star minus alpha star beta.
Where did the trace go?
It was here.
I thought that was after the.
It's all inside the
Oh,
integral.
I see.
I just popped something. And now, since the trace is linear, I can bring the integral inside the trace. But what is this beast? The Fourier transform of the displacement operator, which is the delta function. Ta-da! And as I said, the S-ordered power series I get by tracing with the minus S-ordered delta function. Okay. So we just proved it. Okay. Let's say a few more words. So a question we might ask is, under what conditions are these representations well behaved? When do they exist as a finite function that is differentiable and smooth? Okay, so we're going to talk about one of my favorite topics, existence. So let's just remind ourselves of some things about functional analysis. Okay, suppose I have a function on the complex plane. Okay. I can define its 2D Fourier transform as we have done using our sign conventions as we have so defined them. And then we have the inverse Fourier transform. Okay. So the question is, we might ask, when is the Fourier transform, when it's going to be a well-defined function? And the answer is if the function is square normalizable. Okay, so this exists if I integrate over the plane is finite. And vice versa. So, you know, as you may remember, we think about quantum mechanics in Hilbert space. The space of wave functions is the space of square normalizable functions. If it's not a square normalizable function, then it's not in the Hilbert space. So we often call the Hilbert space associated with, you know, a particle with 1 degree of freedom as L2R. Okay. Right. So remember, so our representations in phase space are these kinds of complex functions over plane. If we look at it, we can think about what we call, if we think about an operator A, on an infinite dimensional Hilbert space, there are a class of operators that is called bounded. They're called bounded. This is a bounded operator called a bounded operator. If the norm of the operator is finite, bounded. Okay? And that inner product, which we can call the norm squared of the operator in our favorite operator space, is the trace of A dagger A. Okay, that's so. If the operator is a bounded operator, is if this Hilbert-Schmidt norm is finite. Not every operator on infinite dimensional space is bounded. But here's an example of a bounded operator. Rho. How do we see that? Let's look at its norm squared, which is the inner product of rho with itself, which is what? Trace of rho squared, which is less than or equal to 1. So it is a bounded operator. Okay. Now, yeah.
Are bosonic Hamiltonians bounded?
Not necessarily. Not necessarily. No. It really depends on the operator. Hamiltonian. Now, we can look at these inner products in phase space. So if I look at the norm squared of an operator, let me write this. Try it this way. Let's look at the symmetrically ordered guy, right? Because the inner product between any two operators is just the product of those, their Weyl symbols integrated over all space with this measure, okay? So for the case of the density operator, this tells me that the norm squared of rho is the square of the Wigner function, which is finite. So the Wigner function always exists. The Wigner function of rho always exists. But what about the other operator orderings? Okay, I should say the following is also true. Remember, if we define the characteristic function as a Fourier transform of the Wigner function, then the trace of rho squared is equivalently the norm squared of the characteristic function. Right? Very good. So what about the Q function? Well, the Q function is the Fourier transform of the normally ordered characteristic function. Okay. But the normally ordered characteristic function I get as the trace of rho with the anti-normally ordered displacement because of this duality, which is either the minus s squared or minus 1 in this case times the symmetrically ordered case. So, what this tells us is that if this was square normalizable, which was the case of the Wigner function, then absolutely the characteristic function of the Q function will be square normalizable, which means the Q function is definitely exists. And we kind of knew that because it was just the expected value of that. So the Q function always exists. But what about the P function? The P function is the anti-normally ordered representation of the state. And the anti-normally ordered characteristic function I obtain by tracing with the normally ordered displacement. But that is e to the plus, which blows up unless this thing falls off faster than this. So this thing is not square normalizable. The anti-normally ordered characteristic function is not square normalizable, and thus there doesn't exist an inverse Fourier transform for it unless this thing falls off. So generally exists only, so the P function only exists if this guy falls off faster than this factor. For a coherent state, this guy is itself equal to that, and this guy then is barely normalizable. It's a delta function, right? If it's a coherent state, the P function is a delta function. So what we have is that generally the anti-normally ordered representations don't exist. Okay. we'll stop there, we'll finish this up, we'll say a few more words about this next time and put this all together. Okay. A lot to absorb, it's a lot of formalism here, but hopefully you begin to absorb it, these relationships, and we'll go from there. Have a good afternoon, everybody.
Are you going back to the characteristic function as exists because trace of growth?
That's correct.
Okay.
So this, because